In today's notes, we're going to continue talking about quadratics. We've been talking about standard form, and we've seen a little bit of what we call intercept or factored form, and today we're going to look at how those two relate and connect to each other. So we're going to start with a warm-up where we're going to look at these 6 graphs, and we're going to match up each of the graphs with one of these statements below. These are all in intercept or factored form. That's the form where we have a binomial times a binomial. And in general, the way that's written is y equals a, and that's the same a as in all 3 forms. So this a is telling us our reflection and our vertical stretch or compression. Then we have x minus, they're often just called p and q, but it's whatever the zeros are. So this is A, same as always. P and Q are the 2 x-intercepts, which we also call zeros or roots. So looking at number 1, it says negative. So we know we're looking for a graph that's facing downward. So that would be either C, D, or E. Then we're going to look at the intercepts. Since we see x plus 3 and x plus 6, we know that those are the opposite of the 2 x-intercepts, meaning my x-intercepts are at negative 3 and negative 6. So E has no x-intercepts, C has 1 positive x-intercept, D has 2 negative x-intercepts. So D is the only possible graph here. It has zeros at negative 3 and negative 6, and the axis of symmetry is halfway between those, which would be at negative 4.5. Number 2, we have a positive a value, which is not stretched or compressed at all, so it's opening up like the parent function. Our zeros are going to be at 2 and 7, putting our axis of symmetry at positive 4.5. So that graph that opens up and has 2 positive x-intercepts can only be graph F. That's the only one that matches that. On number 3, we have a positive a value, so it's opening up. We have x-intercepts at negative 2 and positive 7. If you've forgotten from when we covered this previously, the reason we're taking the opposite here is we're basically saying when is x plus 2 times x minus 7 going to be equal to 0. And the way to figure that out is if this binomial is 0 or this binomial is 0, then the product will be 0. So we kind of break this down into x plus 2 equals 0, meaning x equals negative 2, and into x minus 7 equals 0, meaning x equals 7. So the negative 2 and 7 are actually coming from solving each of the linear factors or the binomials and setting it equal to 0. Okay, so our axis of symmetry here is going to be the average of negative 2 and 7, which is 2.5. To find the average, we add them together and divide by 2. So I have an opening up negative intercept and positive intercept with an axis of symmetry that's positive. Well, that certainly looks like B. We have a negative and a positive. Our axis of symmetry is positive, so that looks very much like graph B. Number 4, we have 2 binomial factors or linear factors that are the same. So the only x-intercept is negative 5. We can write it twice here, but it's really just one x-intercept at negative 5. The only graph that has that is graph A. The axis of symmetry, of course, since both zeros are there, is going to also be negative 5. In the last one, we have an opening downward graph, negative x minus 5 squared, so our solution is 5. So there's, again, only one solution. The graph is opening down with a 0 at 5. That would be graph C. Notice we didn't use graph E. Graph E has no x-intercepts, meaning it's actually impossible to write it in this factored form or intercept form because this form is all about the intercepts. So if there aren't any, it's not possible to write it in this form at all. Okay, our axis of symmetry here is 5, and we'll move on to the main part of today's notes. So we have a graph that we can't tell clearly what the vertex is in this case, but we can clearly tell the x-intercepts are -3 and 2. This tells us that A is equal to 1, meaning we don't need to find out what the vertical stretch or compression is. So we can write this equation as y equals, or f of x equals 1, and then we can write the linear factors based on the x-intercepts, or zeros. So the one on the left gives us x plus 3. That goes with our 0 at -3. And on the right, the one that goes with +2 will be x minus 2. We know that there's a 1 here because it's given from the problem, says a is 1. Now, to turn this into standard form, ax squared plus bx plus c, we just use what we learned in polynomial multiplication. So we can multiply these two using distribution or using the area model. I'm going to use the area model because I think that's like our main tool for Algebra 1 for doing this. So we're going to make an area model. We're going to put x plus 3 on one side and x minus 2 on the other. We get x squared here, minus 2x, 3x, and minus 6. When we combine our two like terms, our final equation becomes y equals x squared plus x minus 6. So that's how we can write an intercept form equation based on the two zeros on the graph, but we do need the a value in order to do that. And then we can just use multiplication or distribution to turn it into a trinomial from the two linear factors that were binomials. Converting, so polynomial distribution. This one, since we did that with the area model, I'm going to use the kind of arrow distribution, the double distribution model like this. So we end up with x squared. Still, let me start over here. So f of x equals x squared, and then this x also connects to the minus 8, so minus 8x. Then the minus 2 connects to x, and then minus 2 to minus 8 will make a plus 16. We combine our like terms and get f of x equals x squared minus 10x plus 16. Next one, I'm just going to do without any model. So this one will be f of x equals, the x's make x squared, the x and the constants make 1x and minus 7x, so that's minus 6x, and then minus 7. By the time you're working on this in Algebra 2 and beyond, they're going to expect you to be able to just multiply a simple pair of binomials like that without using a model or without writing anything down, and just basically going through in your head and saying, I'm going to list out my 4 terms and combine the two that combine. The last one, let's go back to the area model one more time. So for this one, we have x plus 6, x plus 3. We get x squared, 3x, 6x, 18. So we end up with f of x equals 1x squared, a total of 9 for the middle term, and 18 for the constant. As a reminder for standard form, the 18 is telling us the y-intercept. And the axis of symmetry we find by using a and b together. So we do negative b over 2a, and then we can use the axis of symmetry, plug it in to find the k value. Although if we have this intercept form, we usually wouldn't find the vertex from standard form. We would find it from factored form by saying that the axis of symmetry is the average of -6 and -3. So -6 plus -3 over 2 would be -4.5. And then we would plug that into the factored form. So we would do -4.5 plus 6 times -4.5 plus 3. And that would give us -1.5 times +1.5. And that's the same as squaring 15, so we would get -2.25 as our k value. So we don't actually need to go to standard or vertex form to find the vertex. If we have this factored or intercept form, we find the axis of symmetry as the average of the two zeros, remembering that they're the opposite sign. So when we went from here to here, we had to switch the signs to make these the zeros, not the factors. And then we plug in that x value to find the y value of the vertex. All right, this one we're going to figure out where the zeros of each function are. So we're going to plug these things in kind of like a card sort or a matching exercise. So if you'd like to try that one on your own, feel free to pause, try it, and then come back. So here we distribute and we get x squared plus 5x minus 25. When we put the like terms together, they cancel out, and we're just left with x squared minus 25. So that would be this card right here, x squared minus 25. It does say function, which is an equation, so we need f of x. The zeros for that are going to be -5 from this one and +5 from that one. So -5, 5. I do not like writing that as a where it looks like an ordered pair, so hold on, let's not do that. When we're writing solutions and we have multiple things to list, we treat it the same way that we did. So when we're writing multiple solutions, we're going to treat it the same way we did for a discrete domain or range, which is to put the curly brackets and then list them from smallest to biggest. That's how we write a set or a list of numbers. So we'll put -5 and 5 in curly brackets here. For this one, how are we going to do this other than trial and error, considering we don't know how to factor yet? Well, let's do a slight intro to factoring with the area model. So you know how to divide polynomials with the area model. What we're going to do here is divide in a way that's called factoring. The difference between dividing and factoring is that factoring always divides evenly. So if I have x squared minus 4x plus 3, from dividing, I would start over here and then fill in the inside boxes. With factoring, I don't actually know anything outside, but I do know x squared goes here, and I know 3 goes here because it's going to divide evenly with no remainder. That means that this one has to be 3. So now we know that this is x and this is x. The only way to create 3 is either 1 and 3 or -1 and -3. We need to end up with -4x in the middle. So let's see, if I put 1 and 3, then we'd end up with x and 3x, but they would be positive. So we actually need to put a -1 and a -3. Now, this is not a very robust example of factoring. We'll learn this in better detail later, but I'm not sure how I would do this section of the notes without this. So for right now, just consider it dividing like a puzzle with the area model and figure out the numbers that go on the outside. We'll learn a more rigorous, better way to do this soon. So we end up with our factored form as x minus 1, x minus 3. That was this option right here. So we've used up that one, and that one. Our zeros then are the opposite of these, +1 and +3. So we'll do curly brackets, and then smallest to largest would be 1 and 3. It's a very bad curly bracket, so we go out and then back in. There we go. All right, in the next one, similarly, we're going to factor it using the area model. We know that x squared goes here, and we know that -3 goes here. So again, the only way to make the x squared is with x and x. To make -3, I need a 1 and a 3. I know one of them is positive and one is negative. Otherwise, I can't make a -3 by multiplying them. So we're going to look at my middle number here as a positive 2x. So if I have an x and a 3x and one has to be negative, it would need to be the 3x so that my like terms will end up being a negative. So we end up with x minus 3 times x plus 1. That uses up x minus... Wait, oh, I used up the wrong one there, didn't I? Whoops. Let's go back. So I was supposed to, on the earlier one, we used the minus minus. I didn't read carefully. And now we've used the minus plus, but it's backwards. Oh, because I read badly. This is a plus 2x, meaning I need the minus on the smaller number here. Let's go way back here. Where we put the negative. Okay, so we have x and 3x. We need a positive 2x in the middle. I don't know why I thought that was negative. So I need a negative 1x. So we end up with x plus 3 times x minus 1. So now we've used up the other one of these. And our zeros would be, the smaller one would be negative 3. The larger one would be positive 1. And then our last example, our only zero is 5. So that must mean that our linear factors are x minus 5 squared, because we need the same one twice. We don't have two different zeros, we only have one, so that factor must be repeated. And then to multiply it out, I'll get f of x. You can do this with the area model or whatever way, or with the perfect square trinomial pattern from the star chart. We get x squared minus 10x plus 25. Which uses up, well, almost this first one, except we're missing an x here. So x squared minus 10x plus 25, we've also used this. So we filled everything in, and that's the end of today's notes.